All right, so just who am I? So my name is Max. I'm from Finland. I live in Georgia at the moment. Um, I used to work for MySQL AB back in back when MySQL AB existed before it was acquired by Sun and then Oracle. And I work for MariaDB. So I've been doing this kind of stuff for a while. And this is the picture my marketing department loves today. Forced me to put this up every time I do talk. I don't even remember where it was taken. Something. Right, so this talk is going to be about sharding. So I'm going to start by just generally talking a bit about sharding in general, and then I'll focus some more about Spider, which is the specific storage engine in that works with MySQL or MariaDB. So what is sharding? First of all, this is the Wikipedia description of sharding. So a database shard is a horizontal partition of data in a database or search engine. Each individual partition is referred to as a shard. So basically sharding means that you split your database into chunks, and typically these chunks are stored on separate systems, right? So you distribute your database on multiple machines or systems. They, of course, could be virtual machines as well. And that's basically the idea of sharding, right? Splitting it up using multiple systems. Why would you shard in general? We have a lot of customers who do various things, and sometimes we get customers who says, well, hey, we need to shard, and we say, okay, why do you need to shard? Well, management tells me I need to shard. So that's not a good reason to shard. So typically you need to shard if the main reason if the resources of one machine are not enough. So it could be memory, it could be networking, it could be disk size, it could be I/O, it could be anything, but something basically is not enough. One machine is not enough to be able to handle your database load, because we are talking about databases here. That's when you need to shard. You shouldn't shard just because of sharding, because sharding will introduce a lot of disadvantages, which we'll go through in a while. So sharding is not something you should do just for fun, because it's not fun. Typically, especially if you use the relational databases, it's not fun at all, because a lot of the things you get with relational databases kind of disappear once you shard. You can't use them anymore. It's not easy to do joins. It will be very slow and all that kind of stuff. If you use the databases that shard inherently, like something like Mongo or Cassandra, it doesn't matter, because you can't do efficient joins with Mongo anyway. So you don't lose anything, because sharding is kind of built in to something like that. In the MySQL world, there is something called master-slave replication, which has been a part of MySQL for a very long time, already before I started MySQL, which was a long time ago. And this helps with this problem, but it only helps in a certain extent. So if you use master-slave replication, you can scale reads. So it helps a lot if you have a system where you have a lot more reads than you have writes, but you cannot scale your writes. So it helps to a particular of these potential resource problems. However, in master-slave replication, every single machine has to do all the writes, so you don't scale writes at all by using replication. So I'll actually have a comparison, a bit of a comparison later on. So you need to do something else, and this is where sharding comes into the picture. And how you shard has a huge impact on what you can do with the data afterwards. So you need to choose your sharding algorithm and where you shard, because you can shard on different parts of your system as well, and that has a big impact on what you can do with the data afterwards. So what are the disadvantages with sharding? So here's kind of a list. Basically everything becomes more complex, and again, this is compared to having a single relational database server. If you don't have a relational database, these problems typically aren't problems. And some of these problems are solved by different software. For example, by Spider, they do some of these things, but if you don't have any software doing this, you have to do all this yourself. So number one is, of course, increased complexity of SQL. You cannot just easily write a query that spans all the tables, because one table is sharded, it's on multiple servers. You have to figure out, okay, how do you get data from these distributed machines, and how do you join that into one? And in particular, if you want to do something called a join, where you want to join the results of one table with another, and they might be sharded differently, or or something. So how do you do that? And typically it becomes uh, really complex to solve these complex problems, and typically it becomes really slow. So everything you do kind of becomes slow if you shard. And there are ways to get around this. Uh, some good and some bad, but in any case, it will be more complicated because your data is not in a single place. So it's more complicated to get data. It's more complicated to join data and manage data. Also, of course, management complexity, because instead of having one server, you have multiple servers. Uh, what happens if one server is not responding? What do you do? Do you need some kind of HA thing? Do you need to have a multiple copies of all the data? How do you handle that? Again, some systems do that for you, but if you do kind of a homegrown sharding, you have to take care of this yourself. You have to make sure that, well, if a server goes down, does your whole system go down or not? For example, if you just shard and you don't worry about HA, you basically have multiple points of failure. Any server goes down and parts of your data is gone, and typically your data is now inconsistent, and, well, you need to figure out what to do. Same kind of comes with data consistency. Because you have multiple machines, how do you sync the machine? How do you sync these systems? If you have some kind of OLTP system where the state of the transaction is important, you want your data to be consistent. How do you get a consistent read when you have distributed systems? How do you guarantee that it's the same point in time? And that has to do with backups as well. So how do you get a backup that actually gives a consistent view of the system, not just a backup where one server is in time 1 and the other server is in time 3 and the fourth server is in time 4. So especially if the data is sharded so that, let's say, a user account, different parts of a user account can be on different machines, it means that the backup can actually contain the user account in different states, which might be a problem or it might not. So it depends a lot on what kind of data you have, whether you can use anything of this. And of course, operational complexity as well. Right. So before I continue, has anyone done sharding here with MySQL or MariaDB? No. Okay. So when do we need sharding? So as I said, when you run into resource issues. So a simple one is disk space. You have several terabytes of data. Well, disk space itself is not really a problem. You can always buy large disks, but performance typically goes down as your data size grows on disk. So queries become slower, and you basically want to be able to do something faster. So typically here, this is a case where you might need sharding because you can't scale your writes by using replication or something else. Right, and you can also try to use single server partitioning, which helps a bit in certain cases, but it doesn't typically solve everything. Has anyone here used master-slave replication in MySQL or MariaDB? Okay, a few. So if you use master-slave replication in MySQL or MariaDB, so the first thing to know is that it's not synchronous, it's asynchronous. So you have a master, you have to write to the master, and then the writes propagates to the slaves in the master, and there's no, it's completely, I guess, inconsistent. You don't have no way of assuring that your slaves are consistent with the master. You don't know how far behind they are and so forth. So you might have slaves that are far behind your master. But the good thing with replication, and the reason why replication was introduced back in the day, is that if you have a server or a system that has a huge percentage of reads, you can scale by using the slaves because you can read from the slaves. Now, they won't necessarily be 100% consistent with what you just wrote. However, they will be close enough. So it depends on if you have, for example, a blogging website. Well, it doesn't matter if every single customer gets gets the latest comment on every single blog. It's enough that they get something that's close enough to the latest state. So for something like that, you can easily scale by using master-slave replication. So it works well when you have a large number of reads, and well, it's not the solution if you have long execution time for single queries. And of course, each server has to contain the data, so it doesn't split your data; it just splits your reads. So, for example, if you have a system with 90% reads, Um, if you have a system with 90% read and 10% writes, uh, adding 3 slaves means that you now have 4 servers you can read from, so your reads get split into 4, which basically means that your total load on the server, if we assume that a read and a write is kind of the same, which it's not, but making some heavy approximations here, the read traffic goes down to a fourth, so your total traffic per server is now 30% of what it used to be. So if you have one server, and you basically add 3 slaves, you get down to 30% traffic on each machine. So basically you can scale 3 times by adding 3 slaves, more or less. I mean, heavy approximations, but still. So that's a system with 90% reads. So if you look at a system with 50-50, so half reads, half writes, now you can add your 3 slaves. All your read traffic gets divided by 4 because you used everyone to read. But because it was only half of the traffic, you end up with about 62% load. And now you're in a situation where your writes are 80% of all traffic on every machine. So basically you add 3 machines, it costs a lot, and you gain 40% in performance, and you cannot do anything more because you're already at 80% writes. So you can't add any adding slaves won't help your system anymore. So in this scenario, 50-50 already, adding 3 expensive machines and just doing replication might not be the solution because the benefits you gain are not that large. And of course, if you have even more writes than 50%, the benefits go down even further. And this is where you would need some kind of sharding. And then there is something else in MariaDB called, or MySQL called partitioning. Has anyone used partitioning here? One person. So if so basically partitioning means you can split large tables up using some kind of criteria. Actually, these are the partitioning types in MySQL. You can do a range, so define specific ranges, and the MySQL server or the engine will automatically put the data into that where the category it fits in. So you will automatically get a set of files that contain only a portion of the whole table. So here's the range where you define the values. This list where it's very explicit buckets, and then a hash and key where you basically you don't define which values go where. You just say, okay, I want 16 partitions, and they use MySQL uses a hash algorithm to say, okay, which depending on the primary key value or some column hash of a column value, which partition it will go to. And the kind of the benefit with using partitioning is, well, that you can actually then put each individual partition on different disks. So if you have one server with multiple disks, you can put different partition on different disks, and you gain at least some benefits in I/O traffic. Kind of the problems is, well, you still have all the other resources which are shared by the same machine. So CPU, RAM, kernel process, and also in MySQL, all locks are per table. So the locks are not per partition, so concurrency on the table does not increase either. But that's still a useful kind of middle ground before sharding. And also, it's very useful for management purposes. So when you have really large tables, say several hundred gigs, doing any kind of change to the table can take a really long time. It can take days and even weeks. So by having partitioning, it allows you to make changes only on one partition at a time. So it makes the management of the table much more, I guess, usable. Instead of having to wait 3 days to do an auto table, you can do, you have 200 partitions, you do 30 minutes of auto table on each partition one by one. So that's a very good use case for partitioning. Right, so sharding then means basically from MySQL and Spider point of view, sharding is basically using partitioning, and instead of having all the partitions on one machine, you put the partitions on different machines. But sharding can also be done on in other areas. You can do sharding in the application. So already in the application logic, you can have some kind of sharding. Now, uh, sharding doesn't have to necessarily be per table. It doesn't have to be a table that's split up. It could basically be a logical sharding where you have different functionality in different areas of your server. We have, especially in the early days of MySQL, there was no sharding. When you start having a very large application, you realize, well, you cannot put everything on one server. So you say, okay, is there a logical way to split up? I can perhaps put, the analytical data somewhere else. I can have an archive database somewhere else. So I start splitting up my data uh, uh, by some kind of logical split, so that not everything goes to the same server, but I have multiple servers. That's already a type of sharding. So sharding doesn't necessarily mean that you have one table that's split up. Already using different systems for different purposes, which are still tied together in some way, is a kind of sharding. So that's an easy way, but it still, of course, doesn't solve the problem where you have your Facebook or someone like that. You have, I don't know how many millions of, hundreds of millions of users. That is one table. They need to split it up somehow. So there, in a case like this, you of course need sharding, and you can do it in the application, meaning that the application is shard aware, or you build a library of your application where on the application layer the sharding is done automatically for you. Or you can there are third party layers that do this. For example, there's Scalebase and a few others, basically, where they add a layer in the connector. You don't connect to the MySQL server directly, you connect to this external layer, and it will automatically shard your data for you. I guess the drawback of using it, doing it in the application layer is that it gets very hard to do read queries very efficiently, because you will basically have to use your sharding logic to get to the data. Then you can do it on a proxy level. So you have a middle layer that's not at the application, but in between your application and your server, and that middle layer can basically distribute your data. So there are a few examples here: MySQL Fabric, MySQL Proxy, or MariaDB MaxScale. And then kind of the last location where you can do sharding is doing it on the storage engine layer, which is basically behind the database, and that's kind of the focus here of this talk, is doing it in Spider. So you can shard the application layer, proxy layer, or the database layer. And doing it on the database layer, behind the optimizer, has a lot of benefits, or has a lot of potential benefits, because it allows you to do lots of optimizations which you cannot do if you shard on a higher layer. So typically, you have one or two tables that are huge, and you want to shard those, but then you have a lot of smaller lookup tables. You don't want to shard those because you don't need to, but you often want to join, for example, do joins between your lookup table and your large sharded data. And having something that's behind the optimizer, or the optimizer is aware of it, allows you to do your queries much more efficiently than if you do it in, say, in the application logic. Typically, if you do something like this in the application logic, you will just get the data you need from the server and then do the join in your application instead of doing it somewhere below. And here you can actually do the join in the database server instead. So you don't have to send it all the data to the application. All right. So let's look at any questions so far about this stuff. That was kind of an intro to sharding. So let's look at Spider. So for those of you who know the MySQL and MariaDB internals, well, this is kind of an example. If you really simplify the way kind of a query lives in MySQL, you basically have a parser, an optimizer, and then a storage engine. Okay, and the parser, well, it parses the query, it tokenizes the query, and all that stuff. The optimizer, it basically figures out the optimal execution path for the query, and then the storage engine is basically there's an API which basically just transfers data from the storage to the client based on whatever the optimizer chose, whatever execution path the optimizer chose. And this is where Spider comes in. It is one of the storage engines. So it looks like a storage engine. It looks like something you would store locally, but instead of being stored locally, it actually distributes the data to a remote system. So it's below the optimizer in the MySQL architecture. Um, so kind of what Spider, the features of Spider. So it's built by a Japanese guy, Kento Kushiba. Originally, it's actually quite old. It's been developed for almost 10 years now, so it's actually been existing for quite a while. Um, we have it's still not GA, or we don't call it GA. We don't think it's production ready. Uh, do we have customers using it in production? Yes. So it's kind of a mismatch here. For example, there's a MariaDB Enterprise. Spider comes in MariaDB. The community version of MariaDB has Spider built in. However, in the enterprise version of MariaDB, it's still built in, but it's disabled by default because it's not, well, in our opinion, it's not production ready. There are a few reasons why. But we still have customers using it, so we still obviously help those customers. So it's a thing to use with caution, but if it solves your problem, you should use it, kind of. So the basis of Spider is very, very simple. You basically partition tables like you would partition tables locally, but by using the Spider engine, the tables, instead of being stored locally, will be sent to other MySQL servers. So basically, you have a Spider node, which actually doesn't contain any data. It's just contains for the Spider tables. It doesn't contain any data. It just contains the description. It has the partitioning, I guess, algorithm, and then it sends the data to the remote nodes where data is actually stored. And the remote nodes are basically MySQL servers. And these MySQL servers are not Spider aware. So you don't have to install Spider here. It's basically just MySQL servers. You have a table, and the table doesn't know that it's part of a Spider partition table. So that's kind of the really, really simple answer. Of course, there's a lot of Spider does a lot of stuff in the background, which makes it a lot more complicated than this. And you can then query this table locally. It looks like a large table. You query it, and Spider will basically send these queries to the remote servers, which means that there is a small latency penalty you typically pay, because instead of getting to this server, getting the answer, it has to do 2 network hops. Typically, the reason why you shard is because you have so much data, so the extra latency is completely negligible, because you already have really slow. So I mean, if you already have a performance problem when you start thinking about sharding, typically. So adding this network latency is not a big deal. But if you would take a small Spider table compared to having it distributed with Spider or just having it locally, Spider will be slower because of the latency. But when you take a large table where the table doesn't fit into RAM and all that stuff, typically Spider for simple queries will be faster than doing it locally. Spider is completely transactional, and it uses acheive transactions, which is kind of a way of doing distributed transactions, so that you can actually do transactions, and it will make sure that if you roll back a transaction, it will be rolled back on every of these nodes. So it basically maintains consistency across the shards as well. And Spider also has functionality for doing HA built in, which we'll look at later. But you can also use some other HA mechanism, because these shards here are actually MySQL servers. You can use any kind of HA solution that works with MySQL for these. So these could actually be part of a replication hierarchy. These could be part of a Galera cluster or anything. So you can actually do anything here on these servers. So I pretty much went through all of this already. So for the sharded Spider table, no data is stored on the Spider node, but you can of course have other tables that aren't sharded, and those can be stored on this Spider node, right? So when you do joins or combine data from the sharded table to the non-sharded tables, it can be done here on the Spider node. And this is where some of the optimizations comes into place, because you might have some queries where it makes more sense to actually make the joins locally on the nodes instead of making them here. And that's something that you can do with Spider. You wouldn't be able to do that with with another sharding solution where the sharding is done on a higher level. Right. So so basically, what happens when you create a spider table? It creates a link to the remote table, and spider basically when you when you enable spider in your MySQL MariaDB server, it adds some tables to your system tables in MySQL, and one of them is that it keeps track of all the links between the different remote nodes and the local nodes. So every single spider table is a link to a remote table, and the link table can then have any engine. So you could use InnoDB or MyAsm, but you could also use some other engines. For example, there's an engine called TokuDB. Has anyone heard of TokuDB? No. There's an engine called TokuDB, which is typically, so in general for MySQL or MariaDB, the main engine for transactional data is InnoDB. The transactional engine is fairly good. However, InnoDB's performance starts degrading when typically when your data size starts going far beyond your RAM size. So if your data is say 2x, 3x that of your RAM size, well even less if you have large data sets, you start seeing a performance hit in InnoDB. And TokuDB is designed for large data sets. So basically, the performance when your data set is low, the performance of TokuDB will be lower than InnoDB. But as your data grows, the TokuDB performance is pretty much stable, whereas InnoDB will start decreasing when you hit the kind of RAM equals data size. So, for example, with Spider, you could have TokuDB as your engine instead of InnoDB or anything else. And the remote servers, as I said, they're not Spider aware, they're just MySQL servers. They don't know that they're part of Spider. They just know that they get requests and they basically answer those requests. You can also have multiple Spider nodes for the same underlying table, right? So in this example, we had one Spider node, but you could actually have had 3, and because they don't store any data, it doesn't mean that you have to duplicate the data. You just have to duplicate the table definitions that are stored in Spider. And this is used, well, it can be used for scaling, because if you have a lot of queries, if that's what you need for scaling your data is one thing, but you might also need to actually scale your connection load. So you might actually need multiple Spider nodes to be able to just scale all of your connections. And also, it's also used for monitoring. When you use Spider with HA, you might have a Spider node goes down, and then in order to evaluate whether the cluster can continue or not, it needs to check whether there's one partition. If there's that partition is available to the cluster as a whole, and it uses a quorum mechanism, so it needs to have multiple monitoring servers that can that will agree on the state of the cluster. So right. So this is kind of what we went through already. When you create a table on the Spider node or the proxy node, you basically write engine equals Spider, and then the partitioning clause, and then that's basically all you have to do. And then you still have to create the underlying tables on the backend node. So if we look at some usage examples of Spider, so you can one very simple usage is to use Spider as a federation. So basically meaning to access remote tables. So you can actually create a Spider table that has no partitioning, but it accesses a table that's on a different machine. So this allows you to access data from a remote node. And you can also use Spider to actually create 2 copies of the data, because Spider has the built-in HA mechanism. So basically by defining that your Spider table should be on 2 different machines, everything you insert to the Spider table will actually go to both of these tables, right? So you can use Spider to duplicate your data in a table. But the most common use case with Spider is sharding. So you basically create some kind of partitioning scheme in Spider, and then for each partition you define which host this should go to, and then, well, you have sharding. And again, it's using the distributed transactions through the XA protocol, which means that it's completely transactional. And you can also add HA by having multiple copies of each partition. You kind of get HA. So now if one node goes down, you actually have all of the data. So whether you need this or not depends on what your application is doing and you know what your data is. This, of course, doing this will slow it down a bit. You will also need to store all of your data in two places, so you kind of lose some of the benefits of using Spider by having this. But it's there. It's a possibility. Spider is, as I said, included in the community version of MariaDB since version 10.04. Spider is also available on the MySQL server, but you can't get this from Oracle. You have to go to the Spider developers. So Ken Tokushiba, he has his own website for Spider Forum, where you can download a MySQL that has Spider, or then you use MariaDB. So if you download a Spider, if you download a MySQL or MariaDB that has Spider, you still have to do something. You have to install the system tables. There's an install Spider script. It will install the system tables and enable Spider as a storage engine. So then if you do show engines, or if you look at the engines in the information schema, you should see Spider listed here, like this. And you will also see additional system tables in the, Spider tables in your system's database. So these are for Spider tables. Will basically have a list of all the tables that have a Spider and all the partitionings, and then so every single link that you have between a Spider table and a shard will be listed here in the Spider tables. And then this is for monitoring servers, so you can have multiple monitoring servers for each link, so you have a list of those here as well, and so forth. And these are about the XA transactions. Not really things you typically have to worry about at this stage, but when you start going into very complex architectures, this becomes very useful, these system tables. Then Spider adds 93 system variables. I'm not going to go through them all here, but there's a lot you can do with Spider. There's also 4 status variables for Spider, and there's a lot of options. So when you do a create table where you use a Spider engine, there's a list of probably about 90 different options you can actually give in the create table statement to Spider. Again, I'm not going to go through all of them here because there's too many. But needless to say, there's a lot you can do with Spider, and because Spider is the kind of the main goal of Spider is to be able to get performance out of large data sets. So there's a lot of things that you can do, and they depend on how your data has been sharded. Do you have unsharded data, and things like that? So how do you need to do joins and all that kind of stuff? All of these, most of these options has to do with that. So how to be able to kind of go beyond what you can do with the simple sharding, where you don't, where you're before the optimizer instead of being behind the optimizer. Spider also adds some UDFs, the user-defined functions, which allows you to do certain operations from the Spider node. So, for example, Spider Direct SQL is basically a way to sending SQL statements to the backend nodes. Instead of going through the Spider table, you can go straight to the backend tables through this Spider node. So basically, you can send direct queries. If you know because you know how the data is distributed, you know that you only need data from a specific server. You can use this direct SQL and go directly to that backend server. There's also a background version of it, which is kind of more like doing a map reduce. So basically, you create a temporary table and it starts filling the table with the results of these queries. And some other Spider copy tables allows you to copy tables through the Spider engine when you do things like resharding and other things. And well, this flush the monitoring cache. So let's look at a simple example for setting up Spider. So we've installed Spider, we have it available. Of course, the number one thing that you need is more than one server, right? Because otherwise it doesn't make sense. So we have the Spider node there. We create a table, Spider Federation. The key thing here is engine equals spider, and then we have a comment field, and this is where we tell spider where can it find the actual data for the table. So here it's a pure federation table. We don't have any sharding. We don't have any partitioning. We just have a connection, and then on the backend node we have to have the same table with the same definition, and well, it will work like that. That's perhaps a bit boring, so let's look at a more interesting example where we actually do sharding. So here we create a table, engine spider. We have a comment on something with the backend, the backend servers, and then we do partition by, and then for each partition we can list where should this partition be. So we have partition P1 with all these values, and we say, all right, this partition should be on this backend. The second partition should be on this backend, and so forth. So now we've created a sharded table, and this table, of course, will not contain any data, because every time we insert something, it will first use the partitioning algorithm of the optimizer, and then the spider engine will send it to the appropriate backend server. So that's all good. Of course, every backend node has to have this table, otherwise we'll get an error from it. So if we use this, so we do an insert. Here is one insert. We insert 3 rows. We do it on the proxy node, on the spider node. If we do a select now on the spider node, we will see all three nodes, all 3 rows, and typically this will be a bit slower than doing it just locally because you have the extra network hop. Again, the benefits of using spider do not show up with a 3-row table typically. You need to have a few more than 3 rows for that to be any benefit. And then if you log into the individual shards, you will see that each shard will contain the row that they should contain. So basically it works. One interesting thing with this is that you can actually do partitioning on the backend nodes, right? So you can actually when you create the tables here on the backend node, you could actually use partitioning on these tables. Of course, you will only get a specific, a limited range of values for the primary key, but you could further partition this, or you can just partition by hash or something if it makes sense to be able to, if the table is really large, let's say a few terabytes or something, you split it up into three spider nodes. You still have 1 terabyte per spider node, so it might make sense to further split it up on each node by using partitioning, and this works fine with spider. There's no issue. Yeah. Yes, you can. You can chain, yeah. It will of course be slower each time. I mean, you add a network hop each time, but you could do it. And you can do funky things like make rings, and it's not well, you don't want to do that because you have like infinite loops and stuff, but you can do it. Right. And one thing to notice here is that there is no automatic rollback. So I mean, Spider does everything through XA, distributed transactions through XA, but there is no automatic rollback, which means that if you get an error, it won't roll back your whole transaction automatically. You will have to actually do an explicit rollback. Typically in InnoDB, if you get an error, the whole transaction is rolled back. But in Spider, you have to do it explicitly, but you can. So what about replicating from Spider? So what's interesting is that you can actually replicate from the Spider node, because the Spider node, all of your inserts will go to the Spider node, which will then distribute it, which means that the Spider log will have a binary log that contains all of the queries, which means that you can actually replicate from the Spider log to a slave. I mean, this might not work because the reason why using Spider might be that your table is too large, which means that of course the slave will have a very large table, but it is something that you can do. For example, you could have maybe the reason why your sharding is performance mainly, so that it will fit on a disk. It just won't be very performant. That's where you have a live backup of your data if something goes wrong here by replicating from the Spider node. So you will have all of your data here. on the slave. On the slave. You can of course also replicate from the backends. You can have one replica server for each backend, or using multi-source replication, you can actually have one slave that gets everything as well through multi-source replication. Again, kind of same problems with this. If your table is very large, it means that this slave will have a lot of data, of course. But at least you get some parallelism, because you will have for each of these backend servers, you will have one applier thread on your slave. So you'll be able to do all three in parallel on the slave. I mean, backups in general, I said it might be an issue. So backups in general, you can use any kind of backup method for taking backups of the backend. The problem is synchronizing the backups, right? So, for example, you could use MySQL dump or extra backup to take a backup of these, but they won't be synchronized unless you use some kind of distributed locking here, or you have some kind of script that locks everything and then takes the backup and then unlocks it. Otherwise, you won't get these backups synchronized. But you can do something else. You can have replication from each of these. You can use Galera cluster here actually, or something else. But kind of getting a synchronized backup is not the easiest unless you use replication on the spider node. Then it will always be synchronized. So then I said that Spider supports HA. We saw an example of that. So how does that work? Basically, can you see this? Yeah, okay, it's okay. So setting this up is actually very easy. When you partition, for each partition, instead of having one server, you basically have two servers. This means that Spider will automatically copy everything that goes into this partition will be copied to two partitions. So Spider has this built-in HA where you basically can make a copy of each partition, and you decide per partition. You can decide, okay, where should this partition go? It should go to backend 1 and to backend 2 replica here. So now we get this partition on two machines, and same with the second partition. It will go to backend 2 and some other. The other options here are I told you the Spider has about 90 options, so these are one of these options. These have to do with monitoring. When you use HA, the built-in HA with Spider, you also want to have monitoring to be able to recover if there's a failure automatically without having to do any manual intervention. And that's when you need the monitoring here. And this is what these are about. It tells you how to monitor the table. And the link status is a different story. You can actually use Spider to do to do admin operations. You can do alter tables so that you actually take a particular backend offline for a while with this link status. Tells you, okay, this partition now on this server cannot be used. So you change the link status for a partition, which means that Spider knows, okay, this is not active anymore, even though it's part of the partition. So that's kind of what the link status is about. But it quickly becomes pretty complicated, so kind of beyond the scope of this talk. But it's all in the documentation, which is not very good, by the way, but it's there. And here we set up a monitoring server. So you can set up an external monitoring server, which is kind of like a Spider server. And then you have to basically add this monitoring link to the table, which is kind of beyond the scope of this talk. So what about the performance of Spider? So again, all of the things I say here assume that you have Spider tables that are large, so much larger than your RAM. If not, this is typically not true. So generally, with Spider, simple queries will be faster, mainly because your index size will be smaller. So if your data doesn't fit into RAM wouldn't have fit into RAM on a single server, it might fit into RAM on your backend servers, which means that on your backend servers, the searches will be more efficient because all of your data will be in RAM. So typically, queries will be faster, and of course, you're able to do more in parallel. If you have 3 backend servers, it means that if you're looking for a specific row, you have a primary key lookup. Spider will of course know where to send it, so only one server will be part of that lookup, which means that two servers are there ready to do other lookups, right? So you're able to do multiple things in parallel. So your throughput will go up for those types of queries. And queries spanning all shards can be slower. There is an option called engine condition pushdown, which allows Spider to push where clauses all the way down to the backend servers, which is on by default in MariaDB 10.1, but I think it wasn't in 10.0, so basically it's something you want to put on because you want to make sure that. So, for example, if you have a search which warrants a full table scan, the default behavior in MySQL is to send everything to the optimizer, who then basically applies the where clause. And this is fine when you have one instance. But now if you're using Spider, it's not so fine because this means sending everything from the remote server to your Spider node optimizer to evaluate. So that you don't want to do that. You want to send the where clause to the backend node instead and evaluate on the backend node. That's why you won't have to send the whole table over. So that's something you definitely want to enable on Spider. Yeah. No. So it's only on the Spider node that you have to do this. And then joins and complex queries can be a lot slower because of the way MySQL traditionally does. So MySQL traditionally only has one join algorithm, which is a nested loop join, which means that you take, it's basically like nested for loops. You take row 1 from table 1, and then you scan all the rows in the next table until you find a match, then you, and so forth. So it's like nested join loops, nested for loops, which means that it is not very efficient if every time you go one step in the loop, you have to go to a remote server and fetch a row, which means that joins can be very, performance can be very bad. That's pretty much what killed the NDB cluster product when we had that at MySQL AB. So with joins, there are different things you can do depending on what type of joins you have. MariaDB and MySQL now has something called batch key access that can be used. Instead of doing getting one row at a time, you can get a batch of different rows in one time, which will already help a lot because you won't have to do multiple network hops. Because Spider, you can use the Spider UDFs as well. So if you're joining to a table that you can have you join to some kind of lookup table which is fairly small, you can set up Spider so that every backend node has the same lookup table, which basically means that you could do the join locally on the backend nodes and then just send the result of the join back to the Spider server. So using the Spider UDF, you can do that, and that's something we're also looking at, whether we could make the optimizers more Spider-aware, so the optimizer would be able to actually do that or not. But that's something you can do with Spider. So instead of having to do the join on the Spider node, you can do it in the backend node, which means that you get a lot smaller results that sent over to the, and you don't have to do the join evaluation on the Spider node. So you don't have to do multiple network hops, only one. Well, and then if you go to writing queries, well, inserts are typically much faster. That's the whole point with doing Spider, is getting faster insert speed because, well, you have more hardware and it's all distributed. Each one row will of course only go to one of your backend nodes, so inserts will be faster. Updates, it depends because updates rely on doing a read to get the row you want to update. So it depends on what kind of read you have in your where clause to update the row. So updates can be faster, but if you have a multi-table update where you do complex joins, the updates will be slower with Spider as well. So there's kind of the caveat with that. But typically things where Spider is really useful is if you have some kind of I guess time series data where data structure is fairly simple and you do lots of raw inserts, you insert a lot of stuff, and then that's where Spider is kind of excels. If you start having complex hierarchical data and stuff, Spider might not be such a good fit after all. So some more Spider features. There's a complete list here. Basically, all the features available in the Spider engine. Again, it's a fairly long list. I mentioned most of these. So in MariaDB 10, there's an index condition pushdown, which is different from the engine condition pushdown. The engine condition pushdown is for where clauses and where you don't for full table scans, and this is for indexes and bash key access and so forth. There's look at the full list if you're interested. And then a few things to know about Spider. So DDL statements are not synchronized. So if you do any kind of DDL, it's async, and you have to typically do it on every server separately. And the query cache cannot be used with Spider typically. And well, if you have some kind of central, if you want to use the audit plugin or something, you can have a syslog on the Spider node. And same with the user privileges. Of course, by definition, the user privileges are not shared. You have to either do it through replication or something else, or then just not change the user privileges ever. And well, the engine is still not officially GA, at least not in our mind. And if you want more information, you can go to these resources. We have a lot of documentation on our website. There's a forum for this, and well, Kentoku has some documentation as well on his on Launchpad where Spider is maintained. However, they're not extremely up to date, so our documentation is actually better than the one in maintained by him. And he's Japanese, right? So it might be that the Japanese version of the documentation is it's up to date, but I couldn't read it, so I don't know. So I didn't try. But it's still kind of a good place to go. All right, we have 5 minutes left for questions. Any more questions? I mean, you mean like using it as a federation, kind of? Using Spider as a federation, whether it makes sense. So there's nothing to say that it doesn't. It depends on your use case. So if you have, let's say you've already done some kind of logical splitting of your data. You have one server with some parts of the data. You have another server with other parts of the data. But there is a reason to be able to do some kind of comparison or joins. Then it makes total sense to have a Spider table that gets the data from the remote server. So yes, I mean it does make sense. But typically that's for that kind of reasoning, not for performance that you do that then. No, so it doesn't have to be. So MariaDB has Spider built in. MySQL, of course, does not have Spider built in, but Kentoku, so the guy who's in charge of Spider, he maintains a MySQL version of Spider. So if you go to his site, you get MySQL with Spider. And I haven't checked in a while, but he tries to be up to date. But typically, he's 1 or 2 versions behind. So I think the latest 5.5 was 5.5.41, which is the latest, but he might be behind on the 5.6. So obviously, you might not get immediately the newest. When there's a new version of MySQL 5.6, it might be a couple of weeks or months before Kentoku makes an update. But for MariaDB, because it's integrated into MariaDB, we of course, when we make a new version of MariaDB, we make sure Spider works with that as well. Yes, you cannot use a standard MySQL and just run Spider. You need to get the MySQL with Spider built in. Any other questions? Okay, next question gets a USB key. I happen to have an extra one. If I have one. Yes, I have one. Cool. Right. So I mean, that's kind of so how you. It depends very much on your use case, right? So how you what it's kind of what keys do you use to shard. I mean, if you already have an application, you already have a primary key. It's going to be very hard to redesign it, but you know, something like customer ID would be fairly useful to as a sharding because if you do a lot of lookup, I mean, the point is that the sharding key should be something where so you easily end up in only one shard. That's kind of the idea. Then it's more performant. If you shard using something where you don't do lookups on it, it means you almost always have to go to all shards, which means that the sharding key is not efficient. You won't be able to use the fact that you have multiple servers won't give you any benefits because you will have to use all of them each time. The whole point is trying to be able to isolate which server you use each time. Then it becomes more efficient. Then you can use the fact that you have all these servers. So yeah, I mean, you know, I guess customer ID or something, your username in a system is very easy because every time you log in, you have to look at information. You will go to that shard and get everything. And then if you have multiple tables, let's say you have, I mean, something similar to Facebook, right? You have a user account, and then there's every user account has lots of friends. So there'll be like a mapping table. Okay, who are your friends? And then you make sure that these tables are sharded using the same sharding key, so that you will have the same information on the same shards, and which allows you to do things like joins locally. So you can use the Spider UDFs. You don't actually have to do the joins on the Spider node. You can do them locally on the backend node using the Spider UDF. So that will give you a huge boost in performance because then if you have 100 of backend servers, you will be able to do hundreds of these lookups at the same time because you will only touch one server each time. You get this key. Yeah, I mean, a key that is kind of your application uses as well. So you do all your lookups on customer ID, don't shard based on country because it doesn't you know because it doesn't make sense. Then if someone comes and looks for a specific customer ID, well, you don't know which shard it's in because you sharded by country and not by customer ID. So you will have to go to all shards and try to find this customer ID, for example. Yeah. Yeah. So the question was about the high availability in Spider. So that's that's one of the reasons we don't think Spider is production ready yet. So what Spider does, it allows you to store the same partition in multiple backends. So you can, if you partition your table in, let's do something simple. You partition your table in 4 partitions. You can say, and you have, let's say you have 4 servers. You can say, okay, each partition will go to one server and to another server. So you can create pairs, for example, so that each 2 servers will have their own partition, and they will also have the partition of their friend, whatever. And then if one server goes down, because Spider monitors this, Spider will know, okay, well, now we lost this server, we lost this partition. However, because it exists on this other, everything is still available. So we will be running, you will have all the data. Spider will know, because Spider maintains the state of the links, the Spider will know that this main partition is gone, but we have the same partition here. So it will direct all, now that one server will get twice the traffic, because it will get the traffic of its own partition and the traffic of its friend's partition. But you still have everything available. Where Spider is lacking is when you want to get that failed server back. You have to do manual alter tables and stuff to get the failed server back, and it won't have the latest transaction, all that kind of stuff. So that's kind of the thing that doesn't work well is reintroducing a failed server in Spider. You have to do manual things for that. But the actual failure and handling of that works well in Spider. You mean so if the Spider table is maintained in memory? So no, I mean the Spider table itself. I mean, it uses the built-in partitioning functionality of MySQL, so it's not. It's basically all based on the table definition. So it's very small. It's just kind of you saw the partition by statement. That's basically it's in the table definition file, and that's it. And the Spider engine will just know which backend will it needs to go to. Mhm. Yeah, so that's well, it will be in the Spider system table. So Spider will be aware of this, right? So it will be in the system tables. The kind of which table is sharded and which link does it go to. You saw the Spider system tables. That's where kind of it maintains the list of which which shard goes to which remote backend. Okay, we're kind of running out of time. We're over time already. So if you have any more questions, you can come here or I'll be at our booth later on today. Thank you, guys.